Hi everyone, welcome to our channel. In this video, we are going to see about a short channel double gate junctionless transistor modeling including the dynamic channel boundary effect. It is a IEEE paper and here's our team named VAIGAI. The team members are Janani, Preeti Meenakshi and Priyadarshi. We are from Electronic and Communication Engineering Department from Tyagaraja College of Engineering, Madurai.
The introduction slide is about the development of a new model for a specific type of transistor called the junctionless transistor with a short channel and double gates. The model is designed to accurately capture the behavior of double gate junctionless transistor. The researchers found that the transistor's channel behavior changes dynamically with the applied voltage, especially when the channel is short. This dynamic change in the channel boundary significantly affects the transistor's performance. It works by solving mathematical equations related to the electrical properties of the transistor's channel. To predict how the transistor will behave, they developed a mathematical equations based on the channel behavior they found. This equation works for all mode of operations, such as when the channel is fully depleted of carriers, partially depleted, or in accumulation. To ensure the accuracy of their model, the researchers compared their mathematical predictions with the real-world measurements from simulation. Initially, let's start with the double gate junctionless transistor. Double gate is a type of MOSFET device architecture where the channel region of the device is surrounded by two gate electrodes instead of traditional one gate electrode. If an additional gate is present below the channel, then it is called double gate junctionless transistor. The term junctionless refers to the uniform semiconductor material without any doping variations or junctions in the source and drain regions. Now let's discuss about the dynamic channel boundary effect. It describes the change in the effective channel length of the transistor as the applied gate voltage varies. As the gate voltage is increased, the channel region expands closer to the source and drain regions, effectively increasing the effective channel length. This dynamic extension of the channel boundary is referred to as the dynamic channel boundary effect. In this paper, the model attempts to cover both the long and short channel devices by using smoothing functions. A lot of models developed for double gate junctionless transistor, including some recently published work, focuses mainly on the long channel devices. Some short channel models have been developed, but most of them are valid only in the subthreshold region. The ideal limit is 60 mV per decade. The model will introduce some errors when the thickness of the silicon is greater than 10 nanometer and the ND value is greater than 2 into 10 to the power of 19 centimeter per cube. Some physical features that govern the operation of double gate junctionless transistor in the short channel region are compromised due to the higher doping concentration in the source and drain than the channel. The gate and the drain induced dynamic channel boundaries, which is a unique feature in the double gate junctionless transistor, leading to the longer effective channel length than counter the backwards of the short channel effects. They have developed a full range short channel double gate junctionless transistor model based on the channel potential solution of the Poisson solution and Poisson's double integral.
In this slide, we are going to see the potential model with the dynamic depletion. The dynamic extension of the channel length to the source and the drain region due to the gate fringing field. Calculating the solution of the dynamic channel length, the potential of the physical channel under the gate. By solving the 2D Poisson equation, allow us to determine the potential distribution in given 2D region. Approach the boundary condition. This potential distribution is essential for understanding the behavior of electric field and charges in various physical systems, including semiconductor devices like transistors and diodes, as well as in another electrostatic and electromagnetic applications. The equation related the charge density in the semiconductor to the potential, considering the different parameters that influence the device behavior, such as applied voltage, doping concentration, and the physical dimension of the transistor. In this slide, we are going to see the design parameters and methodologies. The relationship between source drain extension length and gate source voltage at a fixed drain source voltage. The goal is to understand how extension affects the MOSFET electrical behavior under different gate biasing while keeping the drain source voltage constant. This analysis helps optimize device performance, mitigating short channel effect, and achieve device characteristic for advanced semiconductor technology. The parameters are source drain extension length, gate source voltage, drain source voltage. The methodologies are fabricate MOSFET devices with varying source drain extension length using semiconductor fabrication process. Apply different gate voltage to each MOSFET devices while keeping the drain source voltage fixed at 1 volt. Measure the drain current for each device at a different VGS value. Analyze the collected data to establish the relationship between L extension and VGS based on the drain current variation. In this another graph, we are going to see the design parameters and methodology. Design a MOSFET devices with the channel width of 1 micrometer. Study the central potential variation with respect to gate voltage at the source terminal. And the parameters are channel width, gate voltage, central potential. The methodology is to fabricate the MOSFET device with the channel width of 1 micrometer using standard semiconductor fabrication techniques. Perform measurements or stimulation to vary VGS and measure the corresponding V center at the source terminal. Analyze the collector data to understand how the central potential changes with the different gate voltage.
In the upcoming slide, we are going to see about the drain current voltage. And in this graph, the design involved are a multi-double gate junctionless transistor with a different gate lengths. Parameter included are gate length and channel with gate voltage. This length just vary to create a device with a different length, and the channel would keep the channel constant for the device, and voltage varies the gate voltage to steady the transfer characteristics. Methodology involved in this is to fabricate the double gate junctionless transistor device with a varying gate length using a specified semiconductor fabrication technique. Perform measures or simulation to measure the transfer characteristics of IDS versus VGS for each device with a different gate length. Analyze the collected data to understand how the gate length affects the device performance, such as threshold and sub-threshold loop and on-off current ratios. Comparing the transfer characteristics of IGT a device with a different gate length to identify the trends and difference. And in this graph, the design involved to set a double gate junction transistor with a different gate to source voltage and measure the output conduction versus drain to source voltage for each device. Parameter included are gate to source and drain to source and output conduction. This gate to source vary to create the device with a different gate bias, and drain to source vary the voltage to measure the output conduction. The output conduction just measure the rate of change of drain current with respect to obtain the output conduction. And methodology involved in this to create a set of double gate junctionless transistor with varying the gate to source voltage, collect the simulated and measured data points representing the output conduction as a different drain to source voltage value for each device with varying VGS. And in this graph, the design involved or conduct a geometral symmetric test to study the drain current when a small perturbation in a terminal voltage under various gate voltage for a semiconductor device MOSFET or a BJT. Parameter includers are gate voltage and a terminal voltage. This gate voltage to obtain a different operating point, and terminal voltage applies small perturbation to terminal voltage while measuring the result drain current changes. Methodology involved is to prepare the semiconductor device for testing, ensure the device is properly biased with the desired VGS value, set the device to stable operating point by applying the desired VGS and measure the corresponding IDs. Apply a small perturbation in the terminal voltage while keeping VGS fixed. Measure the resulting change in IDS due to the perturbation. Collect the data for the multiple perturbation value and record the corresponding change in IDS. At the conclusion, in this paper, we have seen three important things. From that, we have observed that at the low gate voltage of dynamic channel length, it increases the double gate junctionless transistor and impact on drain induced barrier lowering. From the comparison between the model and simulation results achieve a good argument in all operation region for both the long and short channel. Thank you, and thank you for watching our video.